another presentation. I'm going to lead you through some theoretical analysis concerning the problem and also some different experimental approach which we've made. So the assumptions we made on solving this problem is that we have a quasi-static magnetic field, constant, quasi-static in time and in space. Also, we limited it to 35 Tesla, which is very high field, the highest field that was really made on Earth. We have no currents in our liquid, so that the kernel age is 0. Room temperature, constant density of the fluid, and ideal hydrophobicity of the layer in order to make the little small droplet between two droplets negligible. So. Thin layer physics of water fluid is really what people studied, and we have really some results on this topic. An experimental fact that when we reach a critical magnetic field, we see a system of peaks on the surface of ferromagnetic fluid. What was made theoretically is that we have a plane waves approximation with linearity of every participant of the sun. Here you can see the approximation. So the Z is a form of the surface, and the plane axes are X and Y. So the analysis of this problem is really huge, though it can seem rather simple. But here are the key points of this analysis that were made. First one is balance pressure, where cathodic H is a mean derivative of the surface, and M sub N is magnetization on the surface. So, second point is linear representing the B field, H field, and magnetization as a sum of two vectors, where the lowercase BH and M are much smaller than B sub 0 and accordingly H and M. Then the system is linearized by BH and M, and here we come with the most interesting thing in this analysis is a dispersion equation. So, as you can see, we have a dispersion curve for different values of magnetization, and the most interesting curve is this one, where we have a second 0 omega point, which has a kind of a new point of stability, which allows us to see the system of peaks. So, as you can see, the conditions for change of stability are those. So omega squared should be equal to 0, and the first derivative k should be equal to 0. Also, Rosenzweig analysis gives us some critical wavelengths and magnetization. So this is what we're going to check in our theory. Also, what we've seen in previous presentation is following Vimonin's article, changing the lambda critical and making the criterion for splitting. So when it comes smaller than when lambda critical comes smaller than the droplet's diameter, the droplets should fission. First, we measured sigma in our experimental part. It was very simple, like we took some droplets and then measured the mass of each droplet, measuring glass with droplets, with 10, 20, 30 and more droplets, and then measuring the empty glass. Here's what we get for sigma. Then the most interesting thing in our experiments was trying to measuring the magnetization curve. We made a system of two coils, and one coil had a kind of a box with ferrofluid inside it. So we could see how applying magnetic field to the big coil can influence the fluid inside the small one. So here you can see the magnetization curve, and we can see that we haven't reached saturation in it. So because saturation requires paramagnetic fields that we were able to get, but instead we fit this curve with a Langevin curve and counted the saturation saturation. Also, we could see how differential permeability here, what forming can be according to the fit we've already seen. And considering considering my work, I can see that the most interesting part of it is the numbers, because actually we haven't seen any numbers in last presentation, and I consider that this is the most interesting part of it. Like talking about all the analysis and experimental stuff is nothing compared to some numbers that are in this test. So we can see that the order of magnitude for the smallest droplet is 10 to minus second power of meters. So that's why that was not actually reached in the video, and we also couldn't reach it because of magnetic fields. So I suppose this could be the least order of magnitude for a diameter of droplet. And also we counted the critical magnetization. We can see that concerning my experiment, it's actually 5 times smaller than the magnetization of saturation. Also, we checked the video that was shown in this article, in Dimon's and his colleagues' article, and that was provided in the formulation of the problem. And we were kind of surprised that this analysis really works. So we can see that the only approximation we made is that we changed the gradient of magnetic field by just dividing to the height between the magnet and the droplet. So we can see that it really works because they had order of millimeters for diameter of the droplet, and our analysis gives just the same numbers. So I think that's all I wanted to present. And one more point, I would like you to discuss this problem after meeting. Thank you.